Welcome, everybody. Today I'm going to be talking about embracing user-defined literals safely. And when I say safely, we're not talking about sort of like safety critical applications. What we're talking about is not shooting yourself in the foot. So what is a literal? So according to the dictionary, literal is an adjective, not a noun, right? So you don't usually talk about a literal. Literal is one of these things, it's basically all variations on a theme of, saying exactly what you mean. That's that's doing something literally or the literal meaning of something. I did find one definition of literal that is a noun in the dictionary, and this has to do with typographical errors, but that's not what we're talking about today. So we're making up our own definition of literal, that is to say, the computing language community has made up its own definition of literal as a noun, which is a single token representing the value of an integer or floating point character, string, Boolean, pointer, or user-defined type. User-defined types we'll be talking about a lot today. So here's some examples of literals. You've seen these all before. Integer literals like 1, 2, 3, or with a U suffix for unsigned, or with an LL suffix for long, or 1L for LL for long, or 1L for long, or unsigned long. You've seen these before. Floating points, literals, 12.3, 4.56 times 10 to the negative 7, or 2, but that decimal point has got to be there, otherwise it's not a floating point number. Character literals like quote A, if it's prefixed with a capital L, this is not a literal suffix, a literal prefix here, like the L for long characters, or wide characters actually, lowercase u for UTF-16 characters, uppercase U for UTF-32 characters, and string literals, which are enclosed in quotes. And they have the same prefixes that character literals have, and also added, as of C++ 17, I think, the U8 prefix for UTF-8 characters. I'm sorry, the U8 was added, I think, in 11, and it was extended to the character literals in 17 or 20. We have Boolean literals like true and false. Like true and false, exactly true and false. Those are the Boolean literals. Pointer literals, we have exactly one, null pointer. And now we'll be talking about user-defined literals today. Like 59 minutes, or 1, 2, 3, this is a big long, big int, or a regular expression literal could possibly be expressed as a literal, a single token in the language. So what we'll be talking about today is user-defined literals. We just covered what is a literal. We'll be talking about what the user-defined literals are and how we define them, and add new or why we have them, and then how you define them, and then go into use cases for our user-defined literals, and then pitfalls of why it's not as obvious that user-defined literals should be your go-to solution for these things. Sometimes they're not the right thing, or they are the right thing, but you have to be careful what you do with them. All of the examples in here are C++ 17 unless I say otherwise. We have 90 minutes today, so this admonishment actually is a holdover from a previous time I gave a similar talk where I only had an hour. So if you want to interrupt me for questions, that's okay. All right. You're welcome to either hold them to the end or interrupt me for questions. And certainly if I say something wrong or unclear, interrupt me. So a little bit about me. Pablo Halpern, that's my name. I'm an independent software developer. I am a member of the C++ Standards Committee. I have been for quite a long time, so I got to see user-defined literals added to the language. a contributor to this book, Embracing Modern C++ Safely, that just came out at the end of last year. I'll talk a little bit more about the book in a minute. This is my first time at ACCU, presenting or otherwise. I have been to CPPCon since the very beginning and have given 8 presentations there. But my first time here. This is my second time at this hotel for a C++ event. The last time I was here, the ACCU conference had just ended and the C++ Standards Committee was just about to start meeting in the same location. So there was this little overlap where I got to meet some people that were coming to the conference but not to the meeting. So I'm a nerd. I don't know how many nerds you people know. But I do drive a very sexy car, which is a Toyota Prius. Unfortunately, I lost my C++ license plate when I moved to different states in the United States. Each state has its own rules about how you can compose your custom license plate if you care to spend the money for it. And in New Hampshire, where I lived before, it was both inexpensive to get a vanity license plate, and they had a little bit more liberal rules about punctuation than in the current state of Massachusetts. I live in Boston, for those of you who wonder where in the states I might be coming from. I mentioned this book a moment ago. The book is called Embracing Modern C++ Safely, and like I said, that word safely, as you can see highlighted here in the book title in blue here, is, again, it's about being safe as a programmer, not shooting yourself in the foot. It's not about security conscious applications or something like that. Right now, I'm giving this talk about user-defined literals. Earlier today, I think in the previous session, if you had been there, you might have seen John Lakos talk about another chapter of the book, which is the use of the no-except operator and the no-except specifier. And you can, I guess these videos will be available later, so if you missed it and you want to see it, you can do that. On Friday, hopefully, Nina will be giving, no, she's not going to give it at all, huh? Not even virtually. Oh, okay, that is sad. Nina came down with COVID just before this conference. And I haven't seen her in 2 years, and I really wanted to see her, so it's too bad. Okay, but someday she will give that talk. She has given a version of that talk earlier, but this was a much better version. I'm sorry you won't get to see it. All right, so the book is a bunch of, has 3 main sections or chapters. One is on safe features, like just things that make your life easier in C++ 11 and 14 that were not there before the most recent. You know, for those of you who don't know the history of C++, there was this long period from the first standard to the second standard where the language was kind of stagnant. And then in C++ 11, we published the standard, and then it's been at a breakneck pace of every 3 years, a new standard with sometimes huge numbers of sometimes really big features. But C++ 11 sort of ushered in the modern era, and this book talks about C++ 11 and 14 features that still have not made it, not all of them have made it sort of in the general use, and people don't know how to use them right and how to use them without killing yourself. So, what's a user-defined literal? And how do we use them? What are they for? So a user-defined literal is, as the term implies, it's a literal that has a term, a meaning that was given to by the user or by the programmer. So whenever I say user, I mean either the programmer or the person writing a library that a programmer would use. Okay, in both cases are user. Even in the standard, the term user-defined doesn't refer to the end user, it refers to the programmer or to the library. The value of a user-defined literal can be a native type or it can be a user-defined type. So in C++ 11, for the first time, you could have a literal that is for a user-defined type. And the definition is given by the user, like I just said. So the reason we have user-defined literals is as another step to make the language abstractions mimic what is built into the language as much as possible. So we could have if we had our built-in types like ints and unsigned int in this case, you can use operator overloading. I'm sorry, you have built-in operators like less than, and you have the operator overloading that gives you the left shift into an O stream. And that works with built-in types, but it also works with user-defined types. The less than operator for std string, which is a user-defined type by the definition I just gave, works with the same syntax as it does for integers. Okay, so that was the first one of the big things that C++ did for making user-defined types behave more like native built-in types. So user-defined literals are intended to give you the same power with the definition of literals as we got with, say, operator overloading. Operator overloading. My gosh, I'm having trouble talking today. So 5u is a literal for an unsigned value, right? That is a built-in unsigned integer value. So then if we could say that, why can't we say hello with a suffix like s that would say this is a standard string instead of an array of characters that is null terminated, right? So we're familiar with the double quotes being for this array of characters that's null terminated, that's a built-in type. And we want the same thing to work for standard string. In fact, we kind of wish it was there from the beginning. And now it is there as of C++ 11. There are two parts to every user-defined literal token. There's what I termed naked literal. As far as I know, there is no standard term in the literature for it, and certainly no standard term in the standard for it, which is the part of the literal that looks just like a built-in literal. That looks like an integer, looks like a floating point number or a character or a string. And then there's the suffix, which is the part after the naked literal that can be user-defined. So here in the first example, we have the temperature. We have 20.0 underscore C, the implication being that is a Celsius temperature. So that's a user-defined literal for a floating point native format. I don't want to say floating point native type because it's a temperature type. It's not a floating point type. And you can see all the others, right? Now, the third example is a standard literal, which is for hours, which is a chronotype, a type in the chrono library within the standard. And the fourth one is the one I just mentioned, which is for strings. So one thing you'll notice is that we have leading underscores on the first two examples and not on the last two examples. And that's because the last two are standard UDLs. And suffixes that don't have an underscore are reserved for use in the standard. It's kind of the reverse of identifiers, right? You think of an identifier that starts with a leading underscore is probably specific to the implementation and reserved by the implementation. Not all of them, but underscore with a capital letter or double underscores leading are reserved to the implementation. This is the reverse. Without the underscore, it's reserved by the implementation. And in fact, the compilers that I've tried this on have gotten smart and said, if it's not in the std namespace, we're not going to let you do it. You'll get an error if you try and define the user-defined literal without an underscore. Now, there are still these native suffixes in addition to the ones that you can build in, but you cannot define a user-defined literal that matches, like U. U is for unsigned integer. You can't define your own meaning for U. Now, there's other restrictions on user-defined literals. The naked literal, this is really important. The naked literal before the user-defined suffix has to be a syntactically correct literal all by itself. So it's okay to say 0x12, which is a hex number, and then put a suffix on it. And wherever you see underscore UDL, that's a placeholder for whatever a good suffix would be. And I strongly suggest you never use that unless you are writing either slideware or test code or something like that. So, all the examples in that OK line are OK because the thing that precedes the suffix, if you take the suffix away, it would still be a valid literal. The second line, we have this 1.2.3. Well, 1.2.3 doesn't mean anything without the suffix, right? So that's not OK. It's not a valid literal. You can't have, say, a floating point number with 2 periods in it. Null pointer underscore UDL, that's actually an identifier. There's no way for the compiler to say, well, this is a user-defined literal on a pointer literal, right? And the same with false, right? So pointer and Boolean literals, you can't do user-defined suffixes for. It wouldn't do you any good if you could. What could you do with that? It's just an identifier. If you want to create a meaning for that identifier, then give it a value and you're done. All right, the numeric literals that don't fit in the native format, so like a really long integer, that's okay. But the definition, and we'll see later, the way you define the literal will determine whether you really can use a really large value or not. String concatenation rules are special. If you take 2 string literals to normal string literals without any suffix and you put one after the other with just space or nothing in between, it gets concatenated by the compiler into a single string. That is still true if you have a string literal with a user-defined suffix, but the rules are either all of them have to have the same suffix or the ones that don't have no suffix. So you can mix suffix with no suffix, you can mix suffix with suffix if they're the same, but you can't mix 2 different suffixes. So the last line shows us that, if we have UDLA and UDLB, that's an error. But if we have UDL and nothing, that's okay. And if we have UDL in both cases, that's also okay. Before we had user-defined literals, we were still able to program in C++. You might have noticed that. So if we had a case like of IPv4 address class, and we wanted to define a value of that in our program, we would simply call the constructor and pass a constructor argument in, or one or more constructor arguments in, and you would end up with a value. Now, technically, it's not 1 token. It's at least 1, 2, 3, 4 tokens in this IPv4 address. That's 1 token. Open paren is a token, the string is a token, and the closing paren is a token. But it got the job done for the most part. Factory functions were another way you could get the job done. So in this case, we have a class temperature, and we might want to have more than one way of constructing a temperature. And if we want, say, a Celsius temperature, we would create a factory function, Celsius. A factory function is simply a function that returns a value. Its purpose in life is to construct something. And we would pass it the value we care about, and it would construct our temperature for us. And there we see in our last line what it looks like. And it looks kind of like a literal. I mean, it's not all that different conceptually from a literal. This stuff still works in C++11. You probably know that too. But not only does it still work, it's still a good idea in a lot of situations. In many situations, it's still a better idea than using user-defined literals. So be careful about the new toys, because sometimes they're not better than the old toys. Sometimes they're better for some things, but not for everything, and that's the case with user-defined literals. Let's take a look, though, how in user-defined literal land we would do the same 2 examples. In this case, we have our IPv4 address, and we create this thing called a UDL operator that will build our IPv4 address for us. Okay, it returns a IPv4 address. It looks just like a factory function. In fact, technically that's what it is. It's a factory function with a very strange name. And we use it by putting our UDL suffix at the end of a string argument in this case. Similarly, for temperature, the argument now in this case is a long double instead of a string, and the naked part of the literal is a double. Now, this example is just to give you a little bit of foreshadowing of, what the overall picture, but we'll get into much more detail about the multitude of different ways you can actually define the user-defined literal. This just happens to be the most common and simplest example of defining user-defined literals. All right, so is this an improvement over the previous slide? I would say probably, but not a gigantic improvement, but it's kind of nice. It's pretty. So if that's all it is, if these are basically equivalent and we were able to get the job done before, then aren't UDLs just syntactic sugar? What do you think? Yeah, it's just syntactic sugar. No, it's not just syntactic sugar because you shouldn't put the word just in there. And because operator overloading is just syntactic sugar by the same rationale, right? And infix operators in general are just syntactic sugar, right? There's nothing computationally better about A plus B versus plus parenthesis A comma B, right? So syntactic sugar is about readability. It's not necessarily frivolous. But it can also be used to obfuscate. We've seen user-defined operator overloading do really weird things, and there's entire competitions about how badly can you obfuscate code by using all the features of C++, right? Well, user-defined literals just gives you another tool that you could use to write obfuscated code if you really choose to do that. We'll see some examples later where you may even have good intentions and you unintentionally obfuscate something. So how do we define these things? Now that we know how more or less we use them and why they exist, the way you define them is that you define this funny named operator. Operator, open quote, close quote, followed by the name of the suffix that you are trying to define. Okay, so this defines a UDL suffix underscore UDL. Now, you could put white space in two different places in this definition. You could put a white space before the first quote or after the second quote or both. And syntactically, it all means the same thing. But the white space is actually discouraged. In the case of the second place, right here, between this quote and the underscore, you technically could get in trouble by putting a space in there, because if you define a macro underscore UDL, the meaning of your code will change. So could happen, right? If you don't put the space in there, the quotes and the underscore UDL become a single token and the macro won't get expanded. Weird, huh? Who'd have thunk? So my suggestion is just don't put the spaces in there. And if you don't remember where that space could get you in trouble, just don't put any spaces in there. All right. And there should be nothing between the open and closed quotes. If there is, that's syntactically incorrect. Now, the arguments of this operator depend on which form you are defining, and there are 4 different forms. Cooked UDL operators are the simplest, where the naked literal is evaluated by the compiler and then passed to your operator. The raw version is that the naked literal is converted into a null-terminated string, and that is what's passed to your operator. The numeric UDL operator templates are where this is really weird. Until you get to the example, you're going to say, what? The various characters that make up the naked literal are passed individually as template arguments to your operator. And the string UDL operator is where the string UDL operator template is where the string is converted into a user-defined type, which is then used to instantiate your template, the weirdest form of all. Each one of these is harder to write, but conceptually more powerful. Well, the last two are equal in power, but the last one is the hardest to write, and but the cooked one is the easiest to write, and technically the least powerful, but still pretty darn powerful. The raw one is the next harder one to write, and a little bit more powerful, and so on. So let's talk a little bit about namespaces. Even though the definition of the literals doesn't require you to do anything with namespaces, there's conventions that have developed to keep you out of trouble. And the convention is that the thing about UDL operators is that they're looked up using ordinary name lookup, which is to say you cannot qualify the UDL operator when you use it. You can't write, for example, at the bottom here where I wrote 90 degrees, I can't put 90 std : degrees or 90, my namespace : degrees. You can't there's no place to put a namespace here. So you're at the mercy of, this, whatever is in scope at the time, that's what the compiler can see. So the problem is you don't want too many things in scope at once, or you'll end up with name conflicts. So to avoid it, it's recommended that you always put your UDLs into a namespace, or if your class is already in a namespace, into a sub-namespace, so that you can use types in your namespace without necessarily bringing the literals in if you're not planning to use the literals. So in this case, we have two literal operators that have exactly the same name. In fact, they have the same signature. There's a degree here in our temperature literals namespace, which, as you might expect, returns a temperature, and a degree literal in our geometry literals that returns an angle in degrees. Okay, in this case, a double, right? Both pretty reasonable uses of _DEG, right? But you can't have them both in scope at the same time, or you won't be able to use either of them. So instead, what you do is you put them into these namespaces, and you tend to use a convention like, something _literals, so it's pretty obvious what it means. And then you bring that namespace into scope before in the blocks where you use those literals. So if you want to use both angles and temperatures in the same code block, and you want literals of both, you're out of luck. But that doesn't happen very often. They tend to be these huge domains where the literals exist, and you're just writing code, and the reason you need the literals is because you're doing so much in this one domain that you need these literals, so you bring them in. A classic example is the standard chrono namespace, the time literals. There's, you want to be able to express things in minutes and seconds and hours, so you just bring in chrono literals and you go to town. So now let's actually start talking about the actual definitions. So starting with the cooked UDL operators. How am I doing for time? Good, about half hour into it. In the book, I called these prepared argument UDL operators. And that is because even though I thought I had done a fairly thorough search to find if there was a real name for these things, there's no name for these things in the standard. I didn't find one, so I made a term up. Said, the argument is prepared, so I'm going to call it prepared argument. After I'd written that chapter, I started finding that people were latching onto the term cooked as opposed to raw, and it totally makes sense, and I don't know why I didn't think of it myself. So in this talk, I will be referring to them as cooked UDL, but if you buy the book, and I meant to borrow the book, John has the copy of the book with him. I meant to bring it. It's a big volume, but it's organized so cleanly that you're not expected to, nor do you need to read it cover to cover. And like I said, it's organized into these different sections. It's organized, actually I should digress for a moment about the organization of the book. The book has, like I said, three chapters. The first is the safe stuff, which is, just use it and be happy. The second one is what he calls conditionally safe, which is if you use it carefully and you're aware of the pitfalls, it's a very useful feature. And the third one are the unsafe features, which means unless you really have need for it, you probably should stay away from it. But if you do use it, be really aware of what the pitfalls are, because they can really bite you. So this one is in the second category, barely. I mean, it's almost could go into the first category. It's not particularly unsafe, but there are pitfalls and you should be aware of them. Anyway, in the book, I called it prepared argument UDLs, but for now on, it'll be cooked. And if we ever have a second edition of the book, we'll change it. What happens is you have the naked literal and the suffix. As I've said, in the case of a cooked UDL, the compiler completely evaluates the naked literal and then passes the evaluated value to your operator. So in the case here, the example I have, where I have 1tick234.5 underscore UDL. Well, those characters, that 1tick234.5 is a floating point value, is a floating point literal. It's evaluated as a floating point number, and in fact, it's evaluated as a long double, and it is passed to the operator. So the operator here is being called with an argument of 1234.5 long. That's a long double. Now, what was I about to say? The tick mark, that's it. Does everybody know what this means? Okay, see a few shaking heads. Do you have a question?
Why it's passed as a long double? Because this operator takes a long double as argument, because 1, 2, 3, 4, 5 is normally a normal double. Why am I wrong?
Okay, I'll get to that. So the question that was just asked is, why is it a long double instead of a normal double, since the 1234.5 normally would just be a double? I will get to that. Hold that question if I don't answer it by the end. But so I just was getting back to the tick mark, because I did see a few shaking heads. The tick mark is a digit separator. It was introduced in C++ 14, I believe. And it is just to make your, like if you were writing a long number out and you wanted to separate, say, that at the thousands and the millions and the thousand millions, you would put either, depending on your own favorite notation, either a comma with a decimal point or periods with a comma. But in C++ and in C and in most programming languages, the period is the decimal separator. So the digit separator would be something else. We couldn't use comma. Comma was already spoken for in the language. It means the comma operator. So instead, we have we chose this single tick, and that is your digit separator. And it's not allowed at the very beginning, because then that introduces a character literal. But it's allowed between any two digits within your numeric thing. Great for readability, and we'll get back to it, because the fact that it's here is going to be very interesting later on. But in this case, for these cooked literals, the tick mark could be there or not, and the result is exactly the same. And that is true also of the built-in floating point and integer types. The tick marks will not change the value of the literal. So there are 12 different possible overloads for a cooked literal UDL. I'll show you the full set in a moment, but the basic thing is you've got integers, floating point numbers, and And then there are 6 different types of character literal and 6 different kinds of string literals. 5 different kinds of character literals and string literals, right? So there's normal chars and wide characters and character 16, and character 32, and character 8 for each of the character literals and string literals. So that adds up to 12. Now, the thing in red here is part of what I was getting at before when I was talking about that you can use numeric literals that are too big to actually fit in the number. If you're using cooked UDLs, you can't. Or you shouldn't, depending on whether it's floating point or integer. In the case of an integer overflow, the compiler can absolutely totally determine that you have overflowed your integer, and it will give you an error message if you write an integer literal that maps to a cooked literal UDL, and your integer is too big to fit in the largest integer type that the compiler supports. No, not the largest integer type the compiler supports. Long, unsigned long. If your compiler supports some built native integer type that's bigger than unsigned long, you still cannot write a bigger integer literal. For floating point, the compiler is required to sort of truncate it. Like if you have too many decimal places, it's going to throw away the excess precision. It will probably give you a warning. I hope most compilers will give you a warning in that case. But if it doesn't, if it loses precision on translation to a long double, and by the way, a lot of decimal numbers lose precision even if there's only 2 decimal digits. They may not be exactly representable in a binary floating point number, and the compiler will not warn you about that. I don't know any compiler that will warn you about that. But if it's a really long number and a lot of numbers digits after the decimal point or whatever, or a huge exponent or something like that, it'll probably warn you, but it's not allowed to reject it. So you got to watch out for that. But you have to watch out for that with normal literals too. So here's some examples. We have a type that we'll call token that represents something in our system that we're, say a parser or something like that. And it has a built-in, it has a nested type, token type, which is a enumeration having either internal or external, and a constructor that takes an unsigned value and takes one of these 2 enumerated values. Cool. Now we define a user-defined literal called underscore token. And the argument is unsigned long. Again, I'm deferring the question as to why it's unsigned long if your value may not need to be that high a precision. But I will get back to it. But it's always unsigned long if it's an integer literal. And it constructs a token. It passes the value of v in. In this case, it passes it in and it gets truncated to an unsigned. And it always specifies the second argument as internal, because that's just what our literal is going to mean. That's if we want to be able to define one that is an external one, we might define a different UDL with a different name that maybe is an E token or something. Okay, that's the entire definition of our operator. Very easy to understand. It is a factory function that takes an unsigned long argument, constructs a token, and returns it. And here it is that in use, we give it 1, 2, 3, 4, which is an integer literal. That's the native integer literal. And we put in the suffix token, and it calls this function, passes it 1,234 as an unsigned long. If we tried to give it a value that is too big, we overflow the native integer unsigned long, and we get an error. And here you see the tick marks in use. This is a hex number, So we tend to put the tick marks every fourth digit. You're not required to. You could put a tick mark between any two digits. But for readability, hex numbers, we normally like to put the tick marks between groups of 4. And it's a number that will not fit in an unsigned long on a 64-bit, for 64-bit unsigned long. All right, here's the similar example. Now we're defining a string literal. Now, a cooked string literal takes one of the 5 character types, a pointer to one of the 5 character types as its first argument, and the length of the string as its second argument. Again, it's just a fixed, known argument list signature for the literal. And it returns whatever you want it to. In this case, we're defining 2 literals for UTF-8 strings, and they both return UTF-8 strings. Okay, this is an alias for a basic string, a standard basic string where the character type is char8 T. And so it takes 2 different arguments. It could either be a normal char star or a char8 T star, and the length. Okay, now we build one of these things using the suffix, and we take this string, which is a normal char8 string, and it produces a 6-character UTF-8 string. And in this case, we specify the U8 prefix, and because it's the U8 prefix, we will get a char8 T star instead of a char star. And we've got this nice big hex, describing a character in Unicode that happens to be the smiley face or the laughing face here. And that is what we see on output if we output it to a display that can show it. All right, and it's 7 characters long in UTF-8. Trust me on that. It just happens to be the way the encoding works out. So here's our list of 12 possible overloads. And you can define any subset of these 12. And normally you wouldn't define all 12. But you do tend to define them in groups. So if you define the character ones, you either define a char one or you define all 5. Same thing with string. You tend to define either one of them or you define all 5 of them. Usually. Not always. It's up to you. Now, good things to know about these cooked literals. There are 12 signatures allowed, like I mentioned. There is not a 13th. You cannot say, oh, I'm going to pass an int or I'm going to pass it a double. Now, this was a decision that the committee made for various reasons that I was not in the room for, but complexity is part of it. If you're defining a literal for integer types, you very likely do not want to overload it for every possible length. So we defined one length, which is the maximum length, and all integer literals go there. Same with the floating point. So these declarations are actually invalid because they have the wrong parameter type. When you're interpreting the literal, there's no the normal promotion rules don't work. So if you, in particular, if you define, say, a floating point UDL and you use it as an integer UDL, it won't be able to find it. It says here, UDLC, it doesn't exist for unsigned long. All right? It does not do the normal lookup and the normal conversion rules. It will not convert an integer to a floating point for you. Similarly, the character here, it won't find the UDL because we only defined it for wide characters. Okay, we didn't define it for normal characters. So there, even though normally it would widen the character if you were doing a normal function call, it doesn't in this case. And that's a very deliberate decision so that you don't end. So first of all, there's couple of advantages to this restriction, as it were. One is that you could have literals from different namespaces that, so long as they do not overlap in signature, they are distinct. And therefore, you might want to grab a floating point literal from here and an integer literal from there and not accidentally call the floating point literal when you meant to call the integer literal, right? If you, for example, forgot to include the namespace. And the same with the characters and all that. It also means, though, that if you want to be able to write something like this, 1, 2, 3, and have it converted to a double and done that way, you have to do it yourself. You have to write 2 overloads of the literal. And that is what is done in Chrono and all over the place. It's very useful to know that. To often, if you want floating point, you'll also want to define the integer one, even if all it does is cast to floating point and call the other one. Question? Yes, that's exactly right. And I'll repeat the question. If you have, say, if you put a sign in front of, say an integer literal or a floating point literal for that matter, the compiler is going to, the reason it's unsigned long is that it's impossible in C++ to define a signed literal, native or otherwise. And I have a slide about this later on, but since you asked the question now, I will answer it. When you say just a normal, -1 in your code, what you're really saying is literal 1, which is a positive value, and then call the negation operator on that. And that is true of user-defined literals as well. You cannot suck in the minus sign as part of your literal. And that will bite us later on, as we'll see. And sorry? What is? Yes, in the case of floats, the same thing. In the floating point, in the numeric literals, the minus sign is not part of the literal, either for built-in literals or for user-defined literals. And so therefore, you can count on the argument being 0 or more, non-negative. Okay, those are the cooked literals. They are the easiest, and in most cases, it's all you need. If you sort of need to go to dinner now, you will have learned something, I hope, and you will actually be able to use literals. You know enough to use literals for most applications, but there's other things you can do with the more powerful expressions of these. So the signature, there's only one signature. There's no overloads here. There's exactly one signature for raw UDL operators, and that is they take a null-terminated string of ordinary characters, and these ordinary characters are in fact characters from the compiler's character set, which technically could be different from the execution character set. So if you happen to work on an EBCDIC computer, for those of you who even remember that EBCDIC exists, but you're compiling for a computer that uses, say, a Unicode character set, these will be EBCDIC characters, or the other way around. If you're, for example, writing a compiler that cross-compiles for some very ancient IBM machine that uses EBCDIC, the characters are going to be probably ASCII characters, and not the destination character set. But most of the time, they're the same, right? For most people, the execution character set is just a superset of the compiler character set. I just blanked on the name of the, well, whatever. Okay. One thing that's important here is that there's no length passed. If you give it a size t second parameter, you're defining a cooked string UDL operator. We already saw that, right? So the double quoted string is going to call this operator, but the numeric one will call this one. So this is only for numeric values. Why do we not have raw UDLs for strings? Because we don't need them. They provide no benefit over the cooked ones. In the case of the raw UDL operators, what you see is a string representation of the naked literal. So this expression here is going to convert this 1, 2, 3, 4 into a string, including the tick mark. And remember I said it's going to come back to us, and pass it to the UDL. And then the UDL can parse that any way it wants. Are you beginning to see really good obfuscation opportunities here? Because they're there. So let's have an example that's not all that obfuscated. I want to be able to express base 3 integers, right? Because I'm a computer scientist and I use base 3 all the time, right? You know, yes, no, and maybe. Good. All right. So I name my UDL _3 because I can do that because the underscore means this is an identifier, not a number. So cool. _3. I hope the algorithm for taking a string of digits and converting it to a number is not all that foreign to you, but basically we loop through the digits and we take what our accumulated value, multiply it by 3 and add the next digit. So that's what's happening here. We're just adding the next digit and then shift left by, multiplying by 3. Okay, and so we say, okay, is this literal? What is this literal? It's 2 3s and a 1, so it's 7. And so we are asserting that is true using a static assert, and we can use a static assert only because we defined this literal to be const_expr. And most of the time, you want your literals to be const_expr, right? I mean, it's one of the cool things about being able to write. You're writing the exact value into the code. It would be really nice if it could be all evaluated at compile time, since you know the value in advance. It can't always be done. If you're doing it for a user-defined type, for example, your type might be impossible to write a const_expr constructor for your type. But if you can do it, if you can get away with it, it's a great thing to do. All right, but we have a problem, and that is down here. We provided it an invalid. I'm sorry. This is good. 2 2 returns the value 8. In this case, it can be evaluated either at compile time or at runtime because it's in a runtime context. But then we have all sorts of invalid strings that could also be expressed, right? And bad things happen, right? If we pass it in a digit that's out of range, it's going to go ahead and evaluate this algorithm and give us 9. We put in a decimal point. You might think, well, that shouldn't happen, right? This is an integer thing, and this is a floating point number. We didn't specify. We just said we want a **. So this is any numeric literal is going to be parsed by this thing, whether it's floating point or integer. And we put in a value that's too big and doesn't fit into our return type, which is int. Well, it'll just overflow. All right, so let's add some error detection. And how do we add error detection? Well, I forgot to mention in the previous slide here, that's good, I didn't do it, okay. The tick mark, that also would have been processed as if it were a digit. We didn't see an example of that. So the first thing we do is the tick mark is legal, so we want it to remain legal. So the first thing we do is up here, we check to see if we get a tick mark, we're just going to ignore it. And that's generally the right thing to do. And then we check to see if our digits are in range, and if they're out of range, we throw an exception. And you know what? Throwing the exception is just about the only thing you can do. You can't, even terminating is the wrong thing to do. I'll get back to that in a minute. And then if this funny formula here is we're about to overflow. Now, I can't wait until we've already overflowed because that's undefined behavior. So I just detect that we're about to overflow. And you know, I worked hard and did a lot of testing to make sure I got this formula right. So I'm pretty sure it's right. But it says that, yeah, if we multiply by 3 and add this digit in just one more time, we're going to overflow. And we throw an overflow exception. All right. Otherwise, we just do what we did before. And it's the same algorithm. It just has error checks in it. Okay. Now, in this case, our first example has a tick mark in it, but that's okay because we're now correctly ignoring it. Our second example has an out of range digit, and it is detected at compile time. Why is it detected at compile time? Well, it's a context per function. So and we are evaluating it in a context per context, which means it's being forced to run it at compile time. And because it's forced to run at the compile time, it says, wait a minute, we hit an exception. And if an exception is hit at a compile time evaluation, it's no good. The compiler complains. The compiler does not crash. The compiler just complains that this is an erroneous, it's not a compile time expression. All right. But now we don't use a context per here. We have another error, which is our period, which is out of range here. So we should detect it, but it's detected at runtime. Why is this not detected at compile time? Well, the compiler tries to evaluate it at compile time, finds that it cannot, so defers it to runtime, and we get an exception thrown. But I mentioned before that throwing an exception is pretty much the only thing we can do because that is something the compiler will recognize as something that should not happen at compile time. So that's what we really want that. Okay, similarly for a number that's too big, we get an exception at runtime. Now, if we were in C++20, we can solve the problem of getting runtime exceptions by using const eval instead of const expr. And I wholeheartedly recommend this if your compiler is up to date with the new standard. Because, oh, I'm sorry, I thought I'd shut everything that was going to interrupt me off, but I didn't. And I don't have a mouse. Okay, so the icon is of somebody meditating. It really will take me longer to like interrupt the presentation and come back than it would if I just let them in it. Okay, I'm going to talk over it anyway. The const eval, if you use const eval instead of const expr, thank you. Oh, I want that picture. It becomes an immediate expression. It has to be evaluated at compile time, and so all our errors at the end here will be done at compile time instead of at runtime. So this is the best way to solve the problem, but again, it requires a C++20 compiler. So what do you have to watch out for in the raw UDLs? The overflow is not detected by the compiler. That's good and bad. It's bad because you might want it to be, because with the cooked UDL, the compiler does all the heavy lifting. It parses the values, it packages it up for you, gives you a nice floating point number. I mean, parsing a floating point number completely is a nightmare. You know, so if the compiler can do it for you, you want it to. But that's the good thing about the compiler doing it for the cooked UDLs. The bad thing is if you want to do something like an extended precision float or an extended, extra long integer or something like that, you can't use the cooked UDLs. You have to use the raw ones. But then be aware that now it's your job to detect overflow if there still is any. There's only one raw UDL for any UDL suffix. You can't have a separate one for floating point and integer. And if there's a cooked UDL that's found and a raw UDL that's found with the same signature, for the same suffix, then it's going to prefer the cooked one. That might be a good thing. That might be what you want. So for example, if you have an extended precision integer, but you have the same UDL for some other use with floating point numbers, you want the floating point one to be found for the floating point numbers, and then you want your raw one used for your integers. And that's something you could imagine doing, for example, if you want to be able to express really big numbers that might be floating, that you want to basically convert them into some floating point format or something like that. You might be within the precision of your floating point system in terms of the size of your exponent and all that. But you want to express it as a really long integer with lots of zeros at the end. Well, that might be an interesting use of a UDL. Now we start getting into the hard ones. So the raw ones are relatively easy to understand, at least. And even though you have to do so much more work, conceptually, they're not that complicated. This one starts getting complicated. The prototype for a numeric UDL operator template is this thing here in the first box here. We have a variadic list of characters, ordinary characters, and then it returns some type and has no arguments. Note this is also for numeric UDLs only, just like the raw ones were. So what's happening is that you write your UDL like this, as we've seen before, the same example over and over again, but this time it breaks this up into how many? 1, 2, 3, 4, 5, 6, 7 characters, and passes each character as a template argument to the function. Conceptually not that complicated, but kind of a weird thing, right? So that's what's happening. That's what's happening here. The return type, and this is where the power really comes in. The return type can be a type, or it can be some meta function expression that evaluates to a type depending on what the actual template arguments are. And and although that seems like a weird thing to do, it's actually the only reason you're using these template form in the first place, as I'll show in a minute. So we're going to do base 3 again, this time using the template form. But in this case, we're going to the implementation is somewhat more complex. I'll define this maximum here because it just makes it easier for me to do the overflow calculation. And I have a recursive function here. It's an ordinary function, but recursive, where I take there's two versions. Let me talk about this version first. By the way, I should have asked this a moment ago. Is everybody here at least sufficiently familiar with variadic templates to understand this syntax of the char ... C? Anybody not? Okay, good. So it's just a list of non-type template parameters, as they call them, meaning it's not a list of types; it's a list of actual values. All right. So this is what's going to be called, and we're going to have this function. Sorry. This function, when we call it, we're going to instantiate it with some partial result and a character, and then a list of additional characters. So we're going to consume this character, and then we're going to recursively use the rest of this list. All right. What's happening? Because recursion is how you take a parameter pack and iterate through it. You have to use recursion. So the first thing we have is a compile time if, a context per if, and it says if it's a tick mark, then we're going to ignore this. We're just going to call the recursive function. Is that clear? And then if it's not a tick mark, and this happens at compile time, remember, if it's not a tick mark, we check for out of range digits and do a static assert that it's within range, and we do a static assert that we're not about to overflow. It's the same arithmetic we did before, but in this case, instead of throwing, we're going to do a compile time assert. And we can do that because all of the arguments are compile time. In a template instantiation, the template parameters are mapped at compile time, and therefore you can use static assert with them. And then we do our partial calculation. We take our partial result, we multiply it by 3, add in the next digit, so we consume one digit, and then we recursively pass the remaining digits into here. And then our base case is when there's no more digits left, we just have our partial result, which is now our final result, and that's what we return. All right, I hope you can understand that at least well enough to move on. I can't go into it too much more detail without running out of time. The helper templates, okay, so using these, so far we haven't seen the actual definition of our operator. We just have our helper templates, and we use that to create this really simple one-line function call for our UDL operator. It takes the pack, it calls our recursive function, passing it the partial result of 0. So we start with 0 for our accumulator and let it recurse and do its job. And by the way, all that recursion is compile time recursion. It is not happening at runtime. So your performance suffers only while you're waiting for the compiler to finish. The binary code is not impacted. But we can do one better. What if we mostly want to return int, but if the number is really big, we want to return a long. That would be kind of cool. And we can do that. We can do that by actually calling our recursive function and saying, does it fit inside of an integer? If it does, then we'll return an int, otherwise a long. So this, if you're not familiar with the conditional T, you should be if you do any kind of serious metaprogramming, if you do any kind of metaprogramming for the most part, says, given a Boolean expression, compile time, Boolean expression, give me one type or the other type. So given this expression, I'm either going to get an integer or a long, and that is going to be my return type. And then I just call the same function. It gets called twice, but the compiler is probably going to memoize it. So hopefully it's not going to slow your compilation down that much. But again, we all have infinite time waiting for the compiler, right? It's just runtime that we care about, right? I know that's not really true, but hopefully this doesn't slow things down too much. So here we're actually using the power of the template form of the UDL operator to decide what's going to happen at compile time. Are we going to get an integer or a long integer? Now, of course, we could even make it more fancy if we want integer, long, and signed and unsigned even. I mean, it should probably always be unsigned, except that negating an unsigned number is kind of a bad thing. So if you want to be able to put a minus sign in front, so I tend to use signed numbers unless I know the unsigned is what I want. And if I wanted unsigned, actually, I would define a different UDL, _3u. You can do that. So now the things to be wary of here. As in the case of the raw ones, there's only one signature. And the integer and floating point, it's not determined until you call it. So again, so maybe if we wanted to say a base 3 floating point expression. You can do that, right? You have 3 to the negative 1, 3 to the negative 2, and so on after the decimal point. You would need to do the same kind of metaprogramming I just did for the int versus long to determine, except it'd be even more complicated, to determine what is the correct return type. You can't just overload. Again, cooked wins every time if you want overloading, if you want simplicity, if you want the compiler to do all the heavy lifting, if you want to be able to go home at the end of the day instead of debugging your metaprogram. But when you really want need the power, this is the thing you can use. So like I mentioned, there's only one template signature, and the compiler doesn't do very much work for you. It determines validity. That much it does. If you give it a floating point number that has 2 E's in it, for example, it'll tell you that's not valid. But if it has too many digits after the E, it won't help you. And if now again, conflicts, what happens if both a cooked and a raw UDL operator and a template, are all possible matches? Well, it's going to prefer the cooked UDL over the template version. But if you have both a raw and a template version, it's ambiguous. It doesn't have a preference. So if we compare the cooked version with the raw version, the advantages of the cooked version is that we can change the return type based on the content of the token. And we can force the evaluation to happen at compile time, even in a C++ 17 or earlier compiler where we don't have const eval. Now, if the only thing you care about is making sure it happens at compile time and you have C++ 20, then go with raw. But if you have to compile with multiple different versions of C++ or you're stuck with a pre-C++ 20 compiler, the C++ 20 compilers are not really complete yet. I just discovered the other day that my compiler didn't have a feature. Then this is one way of getting a forced compile time evaluation that the raw one doesn't have. The downside is that usually the implementation is more complicated. And it's the most complicated we've seen so far, but we can still get more complicated. Now, this is not an either-or situation. In the case of the string UDL operator templates, they have a different domain, which is that they're in string land instead of numeric land. So if you're trying to decide between the numeric template operator versus the string template operator, it's simple. Are you doing something numeric or are you doing something string? It's not about complexity in that case. All right, I'm going to go through this as quickly as I can so I, can get into some of the other issues here, especially since this is like the most rarefied form where, well, I won't go into it. All right, I already kind of just made a little sigh of disgust, so I need to address that. In the book, we do not give advice, and we do not we don't express disgust. Okay, but this is a talk. I'm allowed to give advice here that I wasn't allowed to write into the book. And so, whereas the book, we might just lay something out and let you draw your own conclusions, and it's pretty obvious that, say, cooked UDLs are easier to use and define than raw UDLs, and easier still than the template ones. Here I'll say, you probably want to stay away from this one. But this is a C++ 20 only feature so far that allows you to define a template for operating on string literals. And you've got the template has a non-type template type parameter of some structured type, Structured type is a standard term. I don't know why they came up with this term exactly. It's kind of a weird, a little bit not very descriptive in my opinion. But the important thing about a structured type is, a structural type, sorry, is that it can be constructed in a const expr context and the destructor is also const expr, and all of its members and base classes are public. Okay, so it's like a subset of certain categories of, it's a very complicated. Oh, this is even worse than the other one. This one I do have to oh, God damn it. Thank you. So first I need to skip the break, and then I have to turn this thing off so it won't keep interrupting me, which is, where is it? If I can remember what its icon is. Oh, here it is, okay. No, that's not it. Well, I may have to live with this, but I can't believe it. I can't find it in a moment. Where is it? Oh, here it is. I just forgot what it was I needed to look at. Okay, my apologies. Oh, shoot. Is it the wrong thing? Okay. All right, so structural types. Something can be built to destroy at compile time, and it has to be implicitly convertible from a native string literal, from a const char star, right? And if it's a class template, then its template arguments have to be deducible from the native string using CTAD, which is short for compile time argument deduction. I'm not going to get into that. That's a big topic in C++, and if I get into it, we'll never be done. But here's an example that actually does use CTAD, so you can maybe get a look. So this is a situation where I created a string literal proxy. It's basically a proxy type for a string literal. I'm not sure why this isn't standardized. It probably should be, in my opinion, but maybe I'll write a proposal. That takes a string, an array. This is the way the string literals should be described in compile time code. It's an array of known size of characters. And it copies that array into its internal buffer, which is the correct size to hold all those characters. And then these two functions are just here for completeness. We don't use them in the example, but they're kind of obvious things you might want to have. Okay, so this thing can hold a string, and it can be constructed at compile time from a quoted string, and its character type is deduced automatically from the, whether you have the U8 prefix or something like that. It cannot store a pointer to that string literal. That might be something that you might obviously want to do. Why does it have to copy it? Trust me, it just does. All right, it's a long explanation about what it is allowed to be done in the const expr function and all that. All right, so now we can create these things, and it deduces. Remember, this is a template, but because of argument deduction, we know that this is a string literal proxy of char, and this is a string literal proxy of ychar, and the length is deduced automatically as well. Good. Very quick example of a structural type. All right, now we're going to create an IPv4 address and an IPv6 address classes, and we're going to create a string literal that automatically determines whether the format of our string is IPv4 format or v6 format, and returns one of these types or the other. I'm not going to write that function for you, but when you actually use it, the first example deduces to an IPv4 address, the second deduces to IPv6 address, and yes, I tested these are valid IPv4 and IPv6 formats. Thank you. So the main benefit of this operator versus a raw string literal operator is that you can change the return type based on the content of the string. So up to now, we haven't been able to do that with strings. Now you can. In the case where you have, again, an overload situation where you have the cooked UDL operator, sorry, did I say raw before? I meant cooked. There is no such thing as a raw string UDL. Whereas there's either a cooked string UDL or the operator template. The operator template is preferred. Now, this is the reverse of what we saw with the numeric ones. I do not know why. All right, now let's talk about the actual use cases. I can't believe I slowed down so much that I've got only 10 minutes left. In the standard library, we have a bunch of new literals that were added in C++ 14. Unfortunately, although the feature was added to the language in C++ 11, we didn't actually use it in the standard library until C++ 14. And C++ 14 puts them all into this literals namespace. So it's std literals. Again, if you import namespace std, you get everything in the standard library, including all the literals. If you import just the literals, you'll get all of the literals, even the ones that conflict with each other. And there are no true conflicts, but there are a few literals that have the same name but different function, like in string versus numeric. And if you include a sub-namespace, you get just those. All right, so for example, if we take std literals, string literals, we can now express hello with an S at the end and get a string. Isn't that what we've always wanted? So you're done now, talk's over? No, that's all we really wanted, right? Just put an S at the end. So that is something in the string literals is the first one I'll talk about a little bit more. We got string literals of the different character sizes, and you've got string view literals of the different character sizes, and they all work kind of the way you would hope they would. Imaginary numbers. So you put an I suffix after a floating point number, you'll get a complex number where the real part is 0 and the imaginary part is whatever came before. So, and then there's variations for float and long double, but by default you get double if you just have the I at the end. So this works for both integer and floating points, but the result is always a floating point complex. So if you see here, if we bring in our complex literals, sub namespace here, we can say for IF and you get a complex of float with the real part being 0 and the imaginary part being 4.0. So this was an integer literal, but you got a floating point complex number. If we do a normal arithmetic here, 5.0 minus 3.2i looks like math, right? Looks like the way you express a complex number, and that's exactly what you get. You get a complex number with 5 as the real part and negative 3.2 as the imaginary part. Cool. There's a very rich set of types that were added into the time library, chrono. Hours, minutes, seconds, milliseconds, microseconds, nanoseconds. These are all integer types, but there are duration types corresponding of all the same magnitudes that have floating point values. And here's the UDL suffix that you'd use. So if you specify 8 minutes plus 5.2 seconds, you get a duration of the correct size, okay? Chrono is a wonderful library, very complex, very broad. One thing to know about it is that the literals appear in two namespaces. They are aliased in the chrono-literals, or simply literals, chrono-literals. Historical reasons, I guess. All right. Added in C++ 20, there were two more literals for day and year, and they're both integer literals. And we don't have literals in C++ 20 for month and weekdays because those just are enumerated, right? There's just 12 months and there's only 7 weekdays names, and they're just enumerated. So that's the standard library and now let's talk about use cases for defining your own. The standard library for me was like, that was use case enough, right? To be able to express hours, minutes, seconds, and strings and so on. But sometimes you want to define your own. So why would you want to do that? One is to solve the problem of type sinks, right? A type sink is when you use a type argument that is too broad. It's, for example, int. Like anything can match an int, right? So here we have an add to inventory, and we have a part number and we have a quantity. But to avoid confusion, our part number is a special type. I'm sorry, our part number, we're trying to avoid confusion, make it self-documenting by using a type def here for part number, but it's still just an int. So it's fine, here's how you use it. But suppose I accidentally reverse the arguments. Well, I'm not going to get a compile time error for that. I may not get a runtime error for that. It may just screw up my database. And here's another situation. Okay, our part numbers say are always 5 digits long. What happens if the first digit is 0? Suddenly that's an octal number. And that may not be what we intended. So int is a type sink. So to avoid that, we define a type part number. It's in this case, this is an idiom for strong type defs. I'm going to run out of battery before I run out of the talk. So when I use it, if I get the things reversed, I've solved the problem. So here we have our user-defined literal here, underscore part that returns a part number instead of a raw int. One thing here to note is this is not const expr because it's calling a function stir to L, which is not const expr. And I'm hoping in the future library stir to L or something like it will be const expr. There's also another function from string. It's also not const expr. So right now, we either have to write our own const expr conversion. But notice that we are always passing base 10 in here, so that octal digit won't cause our problem. And we now read our type. This is now a stronger argument list or parameter list. So if we accidentally reverse things, we get a compile time error. The arguments are mismatched, right? And if we use that leading 0, that's okay, because we're parsing it correctly. Yes?
We have a comment from Peter Summerlad, who says, the comment, the strong type def in enum should be an enum class scope enum to prevent adding part numbers, for example.
Okay, thank you. I will keep moving because I have very little time left. So thank you, Peter. I definitely appreciate Peter's advice on these things. Okay, so arbitrary precision integers. I've actually talked about this before, so I don't think I need to say much more than is already here. Extended numeric types, decimal fixed point numbers. This is a great example that I don't have time to go through too. But let's just say, this is one of those good examples of when to use the template form. We have numbers that we want to represent. I'm not going to go through the implementation. I'm just going to show the examples here. That these are fixed point numbers, and the precision is determined by the actual content of the token. So that's very useful. String-like things like IPv4, UUID, okay? Physical units. We talked about time units. Here we have distance and mass units and so on, kilograms and so on. one of the big uses of user-defined literals is units, and I will mention that. This is what I really wanted to focus on in the talk, and I have 1 minute to do it. Raw UDL operators have to be parsed, okay? So does your code do what it think it does? Well, you know, we mentioned this before. If you don't parse it correctly, you get wrong answers. If you don't put an error checking on your raw UDLs. Sometimes you have obfuscation. This is awfully cute. I'm using tick marks as separators for my IPv4 address. I actually thought this might actually be a good idea. I actually don't think that anymore. Because it's not a number, don't treat it like a number. Also, have you really done anybody any favors? Here's a representation of an RGB value, red, green, blue. Is that actually any clearer than just simply writing out this? And in this case, the compiler is doing all the hard work for you, instead of you having to parse it. Magic values. How often do you put literals in your code? Usually you just assign a constant, give it a name, and use the name, right? So if you're using a type that doesn't need literals, then don't bother with it, okay? And you know, sometimes the only reason you want the literals is to be able to express 0 or the null thing. Well, just give it a name. Signs, we mentioned signs before. Well, here's an example of where that could really bite you. Centigrade. What happens if I say Celsius -10? That's good. So it's -10 Celsius. If I say -10_C and I've normalized to Kelvin, I get a value that's below absolute 0 because the sign is applied too late in the process. So this is a digression that, you know, for those, you know, if the video ends here, that's okay, because I have a little bit of a digression, but I'd like to, for those of you who want to stick around, units is one of the main uses of user-defined literals, to be able to express things like seconds and minutes and distances and so on. But be careful, there's an important distinction between a unit that represents a point in space or time or temperature versus a delta from that unit. If you take 2 points, you can't add two locations. You can't add them, but you can measure the distance between them, so you can subtract them. You can add a delta to a point to get a displacement from that point. And you can, or you could subtract, and you can add displacements together to get another displacement. So this is the situation with our temperature that I was mentioning before. -10C is a point. It's a temperature point. Or is it? Is it -10 degrees from some other base, or is it temperature? You need to distinguish. So the best thing to do is to name things accordingly. So it's problematic when the 0 point is not, the origin is not obvious, as in the case of temperature. But if you look at the chrono library, you'll see that duration and time point are two different classes. And that's very important. You need to know whether you're talking about a point in time or the amount of time that has changed from that point. Best way to deal with this is, in general, the displacements are what we care about, the deltas, but naming helps. Mile marker is a point, mile is a displacement. Degrees Celsius is a point, you know, it's 30 Celsius versus degrees Celsius might be a displacement. I mean, these are examples of, you might need to distinguish them even further to avoid confusion. Premature normalization, another problem with units. This is kind of a big topic, so I'll just mention it very briefly, that if you try and convert everything into a common unit, you may lose precision unnecessarily. Whereas if you can keep the original precision and normalize lazily, then you can keep your precision. And I actually did experiments here, and if you had, for example, a floating point duration, and you're expressing milliseconds and always converting them to seconds, you'll lose precision right away. But if you keep them in milliseconds, you can add 2 millisecond quantities and lose no precision at all. It's only when you add, say, to a second, So using the kernel library, it tries to keep as much precision as you can. In this case, you can add a full second to 10 milliseconds without losing precision, because it converts everything to milliseconds, which is the higher precision quantity. Okay, and Mateus Puss has a number of talks that are good about unit libraries, and you should look them up as CPPCon talks. All right, so the conclusion is that UDLs were added in C++ 11 to close the gap between built-in types and user-defined types. 4 different formats, each one more complicated than the next, than the one before, I should say. Very powerful and flexible, but it can be abused, both to create bugs and also to obfuscate your code. So thank you. I will stay for questions, but we've run out of time.